In our last lesson, we explored the relationship between inverse functions and their derivatives. And in this lesson, we're going to look specifically at two of the inverse functions that we see most often in AP Calculus. And those are the exponential and logarithmic functions. So they are inverse of each other, and we're going to actually look at their derivatives separately. I want to start with the exponential function e to the x. And I think the most powerful way to introduce the derivative is actually to look at the graph analysis of it. So we know that the exponential function starts very close to the x-axis and increases very quickly as it passes through the first quadrant. So it creates a very simple sign chart for us. Since the function is always increasing, our derivative will always be positive and above. And that's not a lot of information to go on. So we're going to look more specifically at the slope as we progress through the x values. So just to remind you, when we're looking at the analysis of a graph of the original function versus the derivative function, the slope of the original function becomes the y value of the derivative function graph. So if we start on the left, looking at our exponential function, we see that our slope is almost horizontal. It's almost even with this horizontal asymptote that we have here. So if it has a a slope value of close to 0, we know that on our derivative graph, the y value will be close to 0 as well. So you can start thinking about that. And then gradually that slope value increases. It's a positive slope throughout. And that slope value increases more quickly as you pass through the first quadrant. So on the derivative graph, those slope values from the original become y values that are increasing more quickly in the derivative graph. And I hope I've done a fair explanation of why when we graph the derivative of e to the x, we get the exact same graph. And that's really unique. The e to the x function is the only function that has its own derivative, or the derivative and the original are equal, other than the function y equals 0. So this should be the easiest derivative for you to remember this year. E to the x, the derivative is e to the x. And I like to say e for easy. The only way that the problems can get a little more complicated is, of course, if we involve the chain rule, which we'll see in our first example. So normally when we have a power function, such as something like x squared, or just to talk more specifically about chain rule, 2x squared, the power would be our outside function and the 2x would be our inside function. With the exponential function, it actually works in the reverse order. The e base is our outside function, and what's in the exponent of the e function is the inside function. So it's going to seem a little backwards when you first start working with e, but I think it'll get more comfortable the more examples that you see. So following the steps of our chain rule, I know I need to do my outside derivative first. The outside function is my e function, and we just learned that it's identical to its original function. So our job is actually to copy e to the negative 2x exactly as it appears. Because remember, when we're doing our outside derivative of e, the inside function, negative 2x, never changes, and that's true for any chain rule problem. We then separately multiply it by the derivative of the inside function, negative 2x, and that derivative would be negative 2. So just cleaning up our final answer, that negative 2 coefficient will go in front, e to the negative 2x. And so an easy way, hopefully, for you to remember how to handle an e derivative is to always copy first. So identically copy that function and then times it by the chain of the inside. And the inside will always be the exponent of the exponential function. I'd like to leave the next two examples for us to work out together in class. So let's look quickly at this, recognizing this limit expression as a derivative formula. And we've done a few of those this year, so hopefully you're getting more comfortable with these. This limit expression is in the form of the specific derivative formula. So there's two things I need to look for. The first is the function, and in this formula it appears before the minus. So our function f of x is e to the x. And since I know this is a derivative formula, they're asking me to find the derivative of that function. And lucky for us, the derivative of e to the x is itself e to the x. And finally, they're asking me to evaluate that derivative at a specific c value. So I look here in the limit in this formula, and that c value is 6. So plugging 6 into my x and my derivative, final answer would be e to the 6th. We're now going to look at the derivative of the log function, the natural log of x, and that's the one that we're going to see on the AP exam. And to do that, I'd like to again discover what that formula is, and instead of doing it graphically like we did for the exponential, we're going to do it algebraically or using calculus for the log function. So we're starting off with our function being the log or natural log function of x, and we're going to do something called exponentiate both sides. So I know that an e function and a natural log function are inverses. So when I put them together, they cancel each other out. But I can't multiply both sides by e or add or subtract or divide by e. I have to do something called exponentiate, which means I actually take both sides of the equation and they become the exponents of e functions on both sides. Then I get that nice cancellation that I want. So the e and the natural log cancel. What we want to do in our next step is to differentiate or take the derivative using the chain rule. I know that an e function automatically requires the chain rule because of its exponent. And we learned that the outside function e, when we take the derivative, we simply copy it times the inside function derivative f of x will give us f prime of x. And on the right side, since the e and the natural log canceled, I just have an x. And taking the derivative of x with respect to x always gives me 1. So since what I'm looking for is the derivative of my function, which was natural log of x, I'd like to isolate this f prime of x. I can do that by dividing both sides by e to the f of x. So f prime of x ends up equaling 1 over e to the f of x, which you might remember that is in reciprocal form, which is what we learned the relationship of inverse derivatives should be. So we're on the right track. Our directions say to replace f of x with its original value, and remember up here in the blue, f of x was the natural log of x. So let's make that substitution in that exponent. When I substitute natural log of x in for f of x, I see that I get another nice cancellation situation here, which kind of rhymes. The e and the ln cancel each other out, and I'm left with just the x in my denominator. So let's write down the final answer. So the derivative of natural log of x is 1 over x, which you recognize again as the reciprocal of what we call the inside function. That's not a mathematical term, but it's the function inside. And that is the function that was inside the natural log in the beginning of this proof. So what that means is when you see natural log of a function, the derivative is not always 1 over x per se, it's 1 over whatever the inside function was. We're going to see that in our first example. So in this first example, we have the natural log of some function other than x. And so when that happens, it will always create a chain rule situation that we need to deal with. So chain rule, the natural log would be the outside function. So I'll start with that derivative. And we just learned it's 1 over that inside function. So it's 1 over that trinomial 4x squared minus x plus 5. So that expression is our outside derivative. And our inside derivative of the trinomial would be 8x minus 1. So since that 8x minus 1 is technically over denominator of 1, I would multiply these fractions. The 8x minus 1 would end up being my numerator because times 1 doesn't change it. And the denominator would be that trinomial. So that's my final answer. And I just wanted to summarize the 2 steps that we need to do anytime we have a natural log derivative. You start with the reciprocal of the inside, so it's 1 over the inside function, times the chain rule of the inside function or derivative of the inside function. Just like in the exponential section, I'd like to skip these 2 examples and do them in class together. Let's look at the recognizing the limit as a derivative. So this is our general formula. We look for the function after the minus, and I see a natural log function. I just learned that the reciprocal is the derivative, so 1 over x, because x was my inside. We see that they've substituted 7 for x, so f prime of 7 would be 1 over 7.